Observe this picture. In this picture, we can see a boy and the shadow cast on the wall. There is a difference in the size of the hands in the shadow and the boy's hands. Even so, we understand that the hands in the shadow belong to the same boy. When we look at the leaves of trees, even though they may be of different sizes, we can easily recognize which leaves belong to the same tree and which belong to different trees. Many times, even if two objects differ in size, their shapes appear the same because there is a proportional relationship between them. Objects or figures that have the same shape but different sizes are called similar. Naturally, similar figures look alike, the only difference is in their size. This difference too is in a fixed proportion. We are going to study similar triangles, similar quadrilaterals and similar polygons, starting with the simplest figure, the triangle. For that, we need to learn a few things first. Here is a situation. Students of the 10th grade brought a ladder to paint a picture on the wall. Then a question arose: how high would one need to climb on the ladder in order to reach a specific height on the wall? Relationship between a specific portion of the ladder's length and the corresponding height on the wall was to be determined. The students took some measurements and recorded their observations. Based on these measurements, they prepared a table. Length of the ladder, height of the wall. Length of the ladder 13, height of the wall 12. Length of the ladder 6.5, height of the wall 6. Length of the ladder 4.33, height of the wall 4. Length of the ladder 3.25, height of the wall 3. Length of the ladder 2.6, height of the wall 2.4. Length of the ladder 2.16, height of the wall 2. Now from this table, they inferred that if the length of the entire ladder is taken as L and the height of the point where it rests against the wall is taken as H, then length of the ladder L and height of the wall H. Length of the ladder L upon 2, height of the wall H upon 2. Length of the ladder L upon 3, height of the wall H upon 3. Length of the ladder L upon 4, height of the wall H upon 4. Length of the ladder L upon 5, height of the wall H upon 5. Length of the ladder L upon 6, height of the wall H upon 6. To find the length on the wall, we need to draw a line parallel to the ground from the point on the ladder to the wall. Let us draw a simplified diagram. This forms a triangle. There is clearly some proportional relationship between the two lengths. We will find it. For that purpose, we will draw a simplified figure of the three-dimensional picture shown above. If we take different points on the ladder and from those points draw lines parallel to the ground up to the wall, we will obtain the corresponding heights we want. Now, how do we find the exact ratio of the relationship? Well, there is a theorem regarding this. Let us study it. But before that, let us recall something from the previous lesson. The ratio of the areas of two triangles is equal to the ratio of the products of their bases and corresponding heights. Turning to our theorem, look at the diagram below. Here, in triangle ABC, points P and Q lie on sides AB and AC respectively. Line PQ is parallel to BC. In such a case, AP upon PB is equal to AQ upon QC. In other words, theorem, if a line parallel to one side of a triangle intersects the other two sides in distinct points, then it divides those sides in the same ratio. Given in triangle ABC, line L is parallel to segment BC. To prove AP upon PB is equal to AQ upon QC. Construction. Draw segments PC and BQ. A part of this diagram looks as follows. Proof. Triangle APQ and triangle PBQ have equal heights. Therefore, area of triangle APQ upon area of triangle PBQ is equal to AP upon PB because areas proportional to bases, equation 1. Similarly, triangle APQ and triangle PQC are equal in height. Therefore, area of triangle APQ upon area of triangle PQC is equal to AQ upon QC because areas proportional to bases, equation 2. PQ is the common base for triangle PQB and triangle PQC. PQ is parallel to BC, this is given. Therefore, triangle PQB and triangle PQC are of the same height. Therefore, area of triangle PQB is equal to area of triangle PQC because areas proportional to bases, equation 3. Therefore, area of triangle APQ upon area of triangle PBQ is equal to area of triangle APQ upon area of triangle PQC from equations 1, 2 and 3. Therefore, AP upon PB is equal to AQ upon QC from equation 1 and 2. In this way, we proved that if a line parallel to one side of a triangle intersects the other two sides at distinct points, then it divides those sides in the same ratio. This is called the basic proportionality theorem. Basic proportionality theorem. If a line parallel to one side of a triangle intersects the other two sides at distinct points, then it divides those sides in the same ratio. By applying this theorem, we can easily find the relationship between a fixed part of the ladder's length and a fixed part of the wall's height. Moreover, the observations noted by the students are consistent with this theorem. Let us solve a few examples. In the above figure, segment DE is parallel to segment BC. AD is equal to 4 cm, DB is equal to 6 cm, AE is equal to 5 cm. Find the length of EC. Solution. DE is parallel to BC. Therefore, AD upon DB is equal to AE upon EC as per basic proportionality theorem. Substituting the given values, 4 upon 6 is equal to 5 upon EC. Therefore, EC is equal to 6 into 5 upon 4 equal to 15 upon 2 equal to 7.5. Therefore, length of EC is 7.5 centimeters. Now, in previous example, find the length of EC if AD is equal to 3x and DB is equal to 2x and AE is equal to 6. Solution. DE is parallel to BC. Therefore, AD upon DB is equal to AE upon EC as per basic proportionality theorem. Substituting the given values, 3x upon 2x is equal to 6 upon EC. Therefore, EC is equal to 6 into 2 upon 3 equal to 4. Therefore, length of EC is 4 units. What did we learn? Basic proportionality theorem. If a line parallel to one side of a triangle intersects the other two sides in distinct points, then it divides those sides in the same ratio. Exercise. Solve the following examples. In triangle XYZ, point M lies on XY and point N lies on XZ. segment MN is parallel to segment YZ? First, XM is equal to 5, MY is equal to 10 and XN is equal to 6. Find the length of side XZ. Second, if XM is equal to 5 and MY is equal to 10, what is the value of XN upon NZ? Fill in the blanks and complete the following activity to find the value of X.